Hi, welcome back to the session. I'm Ishwan Desai, your physics tutor. Now students, here in this today's session, we will be discussing about an electric potential due to the electric dipole, where students we're going to see an equation of an electric potential on the axial line of it, on the equatorial line of it, and even at any general point due to the dipole. And finally, we will be comparing this, the electric potential with the electric field that we had already got in the chapter 1 due to this dipole. So this is what will be the topic of discussion for this today's session. And of course, some questions for the better clarity of the concepts. So let us begin with this today's session. Now here I'm having an electric dipole which consists of a 2-point charges, a negative charge and a positive charge, and the distance of separation is of 2a. And here this is the center of the dipole. Let me just call it to be as a point O, and let us say that negative charge is at some point A, and let this positive charge be at a point B. Now here we are interested in finding out an electric potential on the axial line of the dipole. So let us consider a point P which is at a distance of r from the center of the electric dipole. Well, now here students, we are interested in finding out an electric potential at this point, right? Now if you see students, the electric potential due to a point charge is nothing but 1 upon 4 pi epsilon naught, the charge q over the r, right? Now here students, we know that electric potential is a scalar quantity, right? So what I'm going to do here is that I'll say that the electric potential at a point P will be the algebraic sum of the electric potential at the point P due to this when I consider negative charge, and plus the electric potential at a point P due when I will be considering this positive charge, right? Well, now this is what I will be having. V is equal to V1 plus V2. So let us find out first V1, right? So V1 will be 1 over 4 pi epsilon naught, the negative charge, divided by the distance. Distance is going to be here in this case AP. All right, now what about the V2 students? V2 is also again here simple, 1 upon 4 pi epsilon naught, the charge q, and over the distance, that is BP, right? So that's here the case. Now we have to get an AP and BP, right? All right, so what is AP students? If you just see here, from the middle of the dipole to this point A, it's my A is a distance, right? And from the center of the dipole, right, to the point P, it's the R, right? So what is going to be my AP? It is going to be a R plus A. So that is what I'm going to write it there. Instead of, I will be replacing it, that AP by R plus A. All right, now what about the BP? BP would be students, again it will be R minus this A, that will give me the BP, right? So it will be, again I'm going to replace it, that BP by R minus A, right? All right, so now the things are very simple students. I'll just take out a common out from here, and that will be 1 over 4 pi epsilon naught. Even the charge q I can take it out. And what I will be having students here in this case, I will be getting inside the bracket 1 over R minus A minus 1 over R plus A, right? So that's what I'm having. Now from here on, the things are simpler. You have to just work out whatever thing is inside the bracket, right? You're just going to cross multiply it. So when I cross multiply, what I will be having here in this case, R plus A minus bracket R minus A divided by R minus A into R plus A, right? So when you just open it up in a numerator, the R and R will get cancelled out, and what you will be available with the 2A, right? So that is what you will be having there. And in a denominator students, if you just see, I can use the identity A minus B into A plus B, that I can write it to be as a square minus B square, and in the denominator it will become R square minus A square, and this is what finally I'm having here. All right, fine. Now students, let me just open it up. In the numerator you will see that the charge q into 2A, right, divided by 4 pi epsilon naught R square minus A square. So this is the equation that I'm having. Now if you just see, what is this q into 2A? It's nothing but an electric dipole moment, right, which I can write it by a letter P. So let me just replace it by P. And in the denominator students, right, if I consider, right, in the denominator, let me rewrite it as 4 pi epsilon naught R square minus A square, right? Now what I do students, I'll just consider, if suppose let us say this point P is at some large distance compared to this A, or else the R that we have chosen is much greater compared to this A here in this case, right? So in such a case, students, the a square term will be a very negligible, right? So I can neglect it if I consider r is very much greater than the a here in this case, right? So this equation I can rewrite it to be as 1 over 4 pi epsilon naught the charge q over the electric dipole moment over the r square. So this is what I am having here. Now if you just see, students, electric dipole moment here varies as 1 over r square. So this is what we are having. Now if you want to find out an electric dipole on the axial line, right, at whatever distance, you just put up your r value there, right, and you get the answer, right? Well, now this is easy, right? This is it's very straightforward if you just see. Now what if you're having a point on the perpendicular bisector of this electric dipole? In such a case is how to get it. Let us quickly see that. Now this time we are having a point on the perpendicular bisector of this electric dipole, or else I can say on the equatorial line of an electric dipole, right? So let us consider this point P to be at a distance of some r1 from my negative charge, and let us say this point P is at a distance of some r2 from the positive charge, right? Now this is again a very much simpler, right? If you just see, students, here I'm having a triangle forming. So if I want to get the r1, I can apply my Pythagoras theorem, right? So when I apply a Pythagoras theorem, this side, that is the AP, right, I can write it to be as a square root of r square plus a square. The same way, here in this case also r2 will be the same, right? It will be a square root of r square plus a square. So what will be the electric potential at this point P? It will be the 1 over 4 pi epsilon naught, the negative charge divided by square root of r square plus a square, plus 1 over 4 pi epsilon naught, the charge q, and the distance here in this case is again square root of r square plus a square. Now if you just see, students, right, what will happen? It will get cancelled out. So the electric potential on the equatorial point of an electric dipole is going to be a 0. All right, so this was within 2 to 3 steps we got an answer, right? Well, now I know, students, you must be having a question, right? What if the point is somewhere here, or else what if the point is somewhere here, right? In such a case, you students, how to get an electric potential, right? Now that is what we will be going with the next part, right? We will be finding an electric potential at any general point due to this dipole. So let us do that. Now this time we are interested in finding out an electric potential at any general point due to this electric dipole, right? Well, now let us consider, students, point P at a distance of some r from the center of the electric dipole. Now here, if you just see, students, the position vector OP is creating some angle theta with the electric dipole moment, right? All right, now students, we are interested at this point P. Okay, well, now let me just consider this point P is at a distance of some r1 from my negative charge, and let us say this point P is at a distance of some r2 from my positive charge. All right, now students, what will be the electric potential at this point P? I can write it to be as electric potential over here case will be 1 upon 4 pi epsilon naught the negative charge over the distance of separation, that is I have chosen to be some r1, all right, plus 1 over 4 pi epsilon naught the positive charge, and the distance of separation that I have chosen here is r2. So this is what the equation I will be getting. Now students, here in this case I'll just get the common term out, and what I will be getting here is 1 over 4 pi epsilon naught. If I take the charge q out here in this case inside the bracket, I can write it to be as 1 over r2 minus 1 over r1, right? So this is what I am having. Now what I do, students, here I'll be just taking that 1 over 4 pi epsilon naught to be some k constant, which is the electrostatic force constant, right? Instead of writing that one again and again, I'll just replace it by some k constant. So here this is what I'm having here. I'll be getting this equation to be as kq 1 over r2 minus 1 over r1. All right, now students, we have to get this r1 and this r2 so that we can substitute over there, right? Now here, if you just see, students, right, I'm interested in finding out a BP and this AP, right? Now what I do here, students, I will be just drawing a perpendicular to this position vector OP, and this is the perpendicular that I have drawn, and let me just call this M be a point over here. If you just see here, students, right, I can very well say, students, this time the MP will be equal to my BP, right? Now, how to get a BP, right? So if you just see, students, here we are having a triangle OM and B, right? So this is the hypotenuse side, this is the perpendicular side, and this is the adjacent side, since this is a theta over here, right? Now, how to get an adjacent side of this? We are having a trigonometric identity, right? Which identity? So we are having a cos theta, students, that is the adjacent side upon the hypotenuse side. So hypotenuse side is my A, and I want the adjacent side, right? So adjacent side will be a hypotenuse into cos theta, so it will be A cos theta. This is what I am going to have, that is the OM, right? Now, can I get a BP? Yes. If you just see, students, here in this case, OP minus OM, that will give me a MP, right? So I have got now my BP, which is nothing but a MP, right? So all right, so I have got an R2 here in this case. Now, students, what about the R1, right? So here also, students, let me just draw a perpendicular line like this. Now here in this case, let N be a point, right? And from the geometry, this is going to be my angle theta, which will be the same as this angle. Now here in this case, this is the perpendicular side, this is the hypotenuse side, this is the adjacent side, right? So we are interested in adjacent because I know, students, AP is equal to NP now, right? So what will be adjacent side? It will be a cos theta. And here in this case, students, now, right, what will be NP? It will be R plus this adjacent side. Yes, so that will be a R plus a cos theta. All right, so now we have also got a R1, right? So now I will be substituting at these places. So what equation I will be having? It will be electric potential K, the charge Q. Inside the bracket, we will be having 1 over R2, right? And what is R2, students? It is R minus a cos theta. And what is R1? It is R plus a cos theta. All right, so now again, students, the things are simpler. We have to just work out whatever thing we are having inside this bracket. We're going to cross multiply, right? So when I cross multiply, students, what I will be having here? R plus a cos theta minus of inside the bracket R minus a cos theta. In the denominator, the multiplication of this two denominator. All right, well, now, students, if you just open up this bracket, right, what will be happening? The R and R will get cancelled, and in the numerator, we will be having a 2 times the a cos theta. And in the denominator, we are going to use the identity, right? A minus B into A plus B is equal to A square minus B square. Using that, I can write it to be as a R square minus A square cos square theta. And this is what I'm having here. All right, so now, students, let me just open it up here in this case. If you just see, what I'm having, K times the Q into 2A cos theta divided by, it is going to be R square minus A square cos square theta. Now, once again, students, Q into 2A, I know it's the electric dipole moment, so I can replace it by a P, right? And this is what I'm going to have a equation. So this is the equation that we had got, right? Now, if you just see, students, here, if I say this R is much greater compared to this A value, right? So what I will be getting, students, I can, students, if I just rewrite it, this equation as a KQ, okay, K P cos theta divided by, if I take this, R square here common out, okay, let us say here in this case, I can write it as a R square in a bracket 1 minus, A square cos square theta by R square, right? So this is also again the same thing, right? If I consider, students, R is very much greater than A, in that case, the term that you see, A square cos square theta by R square, will be a very negligible. And in such case, students, my equation will look, electric potential will be KQ, K, the electric dipole moment, cos theta divided by R square. So this is the equation to make a note. All right, so well, now here, students, if I want to write it here, I can also write it in a vector form, since my electric dipole, right, it's a vector, right? So I can write it to be as, students, K electric dipole moment vector P dot unit vector R, which is along the position vector, that is OP. All right, so if you remember, students, the dot product, when you're having two vectors, vector A dot vector B, that can be written to be as a magnitude of A into magnitude of B into cos theta, right? So when you will be opening it up, vector P dot R cap, unit vector, right? So it will be a P dot 1 cos theta. So that is again going to be a same, and this is what we are having here. Now, students, here, if you just see the equations that we have got for an electric dipole, right? It's 1 over R square, right? So a point to make a note from here in this case. Now with this equation we will be discussing in comparison with the other things. So let us quickly do that. Now students, here we are having this equation for an electric potential, right? The very first thing, students, if you just see here the electric potential, right, it just doesn't depend on the R value, but also depends on the the theta here, right? That is the angle between this position vector and the electric dipole moment, right? Now students, if I just keep this R fixed and even the theta fixed, right? So if I just try to move this point like this, you can imagine, students, we are having a one cone. Just for your visuals, guys, you can imagine a cone and you are just moving that point P on the surface of that cone, right? So all the points that you see on the cone, we will be having the same electric potential. Now of course, if you are decreasing the R by keeping the theta fixed, so here these are the points. At this particular point we will be having some other electric potential, and that will be the same throughout all these points here. So what is happening here, if you just see, it is going to be along this axial line we will be having a symmetry, right? Well, now this is just for your visual, students, right? Of course, as R and theta varies, the electric potential in the surrounding also is going to vary, right? Well, now one more point to make a note, students. We saw that electric potential for this dipole varies as 1 over R square, right? And if you just see, student, the electric potential due to a point charge, it was 1 over R. So that's again a point to make a note. And students, if you just see this now, the electric potential equation, right? The theta here we know it's the angle between the position vector and a dipole in a moment, right? If I consider a point on the axial line of the the dipole, right? The theta here in this case will be a 0, right? The angle between the position vector and the electric dipole moment is going to be a 0. So what will be the electric potential? I will be having cos of theta. Cos of 0 is going to be a 1, right? So that will be giving me a electric potential to be a positive. All right, well, now students, if I just take this point on this side, in this case, students, what I will be having, right? If you just see, electric dipole moment is pointing in this direction, the position vector is exactly opposite of it, angle between them is a 180 degree, so cos of 180 degree is -1. So the electric potential at this point will be a negative, right? All right, so now what about this equatorial line? So when your point is on the equatorial line, the angle created here is 90 degree and cos of 90 is 0. So the electric potential on the equatorial line of a dipole is going to be a 0. So once again, students, you are getting all the possible cases with this equation that we are having here. Well, now students, if you just see here, this is the picture that we are having here in this case, right? Which is the electric field lines. You can very well see the direction of the electric field lines. Now if you just see, students, on the equatorial line, right, we had got the electric field is some non-zero value, right? But the electric potential that we have got is 0. Now again, students, it can be very well explained, right? It's a very simple, students. If you just see, when we define an electric potential, you remember we consider a unit positive charge moving from infinity to that particular point against the electrostatic force, right? So let us say if you're bringing a charge from, students, infinity to this particular point on the equatorial line, let us say, right? So just see the direction of the electric field. The direction of the electric fields are like this, and the displacement is happening here in this perpendicular to the force that will be exerting on it. Yes, and in such a case, students, the work done will be a 0, right? And if the work done is 0, in that case electric potential will be also 0. Now what about if you consider a point on the axial of this, on the axial line of the electric dipole? Look at the the direction of the field lines. They are pointing in this direction, right? And you're going to move that positive charge from infinity, there will be some work done against the electrostatic force, and that will be a positive potential here in this case. Now what if you're placing a point over here this time, right? So look at the direction of the field lines, and you're going to bring that positive charge from infinity to that particular point, right? So here in this case, for sure it will be a negative. This is how it can be very well explained. Now students, we have discussed about the electric potential in all possible ways, right? Now it's time to go for questions. Let us quickly see that. Now students, if you just see this question, it says there are two charges negative Q and positive Q are located at point 0, 0, minus A and 0, 0, A respectively, right? And students, there are again three parts for this question. So let us take them one by one. If you just see, students, the very first question, what is the electrostatic potential at the point 0, 0, Z and x, y, 0, right? So here in this question, students, if you just see what have been given to us, we haven't given the location of the charges. A negative charge is located at this coordinate 0, 0, minus A, and the positive charge is located at 0, 0, A, right? And we have also given the coordinates of the point, okay, where we are interested in finding out an electric potential. So let us first start at this particular point. And to do it, students, I'll be just taking my this, x-axis, y-axis and z-axis here, Cartesian system. If you just see, we have to first of all put up the charges, right? So the negative charge, students, is at location of 0, 0, minus A. So that will be on my z-axis, right? Since x and y, the points at 0, 0, right? Coordinates. So here in this case, I'll be just having a negative charge somewhere here on my the z-axis. So the coordinates of this 0, 0, minus, right? What about a positive charge? It will be on the positive z-axis, and the location here, it is going to be a 0, 0, positive A, right? Well, now students, if you just see, students, it is like, we are having an electric dipole, right? We are having a 2-point charges, right? Negative charge and positive charge separated by a very small distance, let us say, and I can consider this origin here to be as a center of my electric dipole, right? Well, now this time, students, we are interested in finding out an electric potential at this particular point. Well, now if you just see, students, here, right, here again 0, 0, Z. So let me just mark a point P here on the Z axis. Let it be at some point P here, right? And the coordinates, we know the coordinates of this location is 0, 0, some Z distance, right? Well, now how to proceed with this question, right? It's again a very simple, students. We know that the net electric potential, right, at a point P will be the potential due to the positive charge, right, plus the electric potential due to a negative charge, I'll say, right? Yes, let me write it like this. Now, the potential due to the positive charge, right, I know it is going to be a some k constant, that is 1 upon 4 pi epsilon naught, the charge, positive charge, divided by distance, of that point P from the positive charge, right? So I know that from O to P, it is going to be a Z, and from the positive charge to point P, it is a A. So it will be a Z minus A, plus the electric potential due to this negative charge, that will be, students, K, the negative charge, right? That will be a negative charge divided by the distance from the negative charge to the point P. I know it is OP is Z, right? And from this O to this negative charge, it is A. That's a negative A. On a Z axis is negative A, right? So I have to add it up, right? So it will be a minus of minus A. So that will be getting added up there, right? Well, now students, from here on, things are simpler. I can take the KQ out, right? Inside the bracket, I will be having 1 upon Z minus A, right? And this will become minus into minus plus. So, it will become minus of this negative charge over 1 upon Z, and here minus into minus is plus A, right? So this is what, I will be having here. Well, now students, from here on, I have to just cross multiply here, whatever thing is inside the bracket. KQ, it will become Z plus A. And when I just multiplied here, it will become minus Z and my plus A divided by, this is going to be a Z minus A in the denominator and Z plus A in the denominator, right? That is what I'm having. Now, from here on, students, it will be a KQ. I can say Z and Z will get cancelled out. So in a numerator, we will be having, students, it will be a 2 times the A. And in a denominator, students, I can use my identity, right? So that will give me a Z minus A into Z plus A. So that will be a Z square minus A square. So this is what, the electric potential I'm having, the net electric potential at a point P. And again, students, if I want, I can also write it in terms of electric dipole moment. So the net electric potential, right? I'll just write it here, students. The net electric potential, okay, at a point P. I know that product of Q into 2A is electric dipole moment. So that will be a K electric dipole moment divided by Z square minus A square. So this is what, I'm having the final equation, right? So this is the electric potential at a point P. Well, if you just see, students, we are getting a positive electric potential, right? Now, what if, let us say, if you had a point closer to the, the negative charge, right? It has not been asked, but still, students, I'll just, consider here, right? What if, you are having the point somewhere here, let us say, right? Negative, close to the negative charge, right? In that case, students, the coordinates would have been 0, 0, minus z, right? And the electric potential, students, that we would have got is, students, the net potential here in this case would have been, I will just write it here, okay? The net potential, right, at the point P minus Kp divided by z square minus a square. So this would have been the answer. It would have been negative, right? Well, now, students, we have done this, mathematically, using this step, right? Even, students, you could have, used the direct formula, that we had obtained, right? A general formula, right? That is the, students, a very easy formula, right? That you can straight away, you can apply that also. So if you just see, students, which formula, the electric potential, we know that it will be Kp cos theta divided by, and here in this case we are having z, right? So I'll be just writing, that z to be a some r. Okay, so in that case, okay, I'll write it as a z only. So that r is z here in this case, z square minus a square, right? So this I can use it, yeah. And, students, if you just see the electric dipole moment here in this case is from negative charge towards a positive charge. That is the direction of an electric dipole moment, right? And the theta here that we consider is the angle between the electric dipole moment and the position vector, right? If your point P is on the positive z axis, right? So the position vector is also in the same direction of the electric dipole moment. In that case, students, the theta will be 0 and cos of 0 is 1. So we are getting the same as the answer here, right? And, students, if you just take it here, the point on the closer to the negative side. So electric dipole moment is going up, right, towards the positive side, and the position vector is exactly opposite to that. So in this case, students, the theta would have been 180 degree. And again, you are getting this answer. So again, this is also a, very, within 1 minute, you are getting the answer, right? Well, I have just shown you guys both the ways. Okay. So, so this is the first part of it. Now, let us go for the next second part of it. That is, we are interested in finding out an electric potential at x, y, 0. This is the location, right? Well, if you just see, students, looking at the coordinates, right, I can very well say that, this point will be lying on the xy plane, right? Because the z here, if you just see, it's a 0, right? So that means it's like, when you're having a one plane, right? You can just, see here, this is my xy plane, and your point, any point, will be lying here on this xy plane. Let me just consider the point somewhere here. Okay, you can consider it any distance. So if this is a point P, right, and let me just mark it the coordinate x, y, 0, right? So here in this case, students, if you just see the distance at which the point P is at, right? So I can just draw a line like this, right? If this is going to be a distance, let me just call this x be a some distance, right, from the positive charge. Even if you just try to take, distance from negative charge to the point P, it will be a same distance, right? So here in this case, both will be a same distance. So what will be happening? The electric potential at a point P, due to this both the charges, one is positive charge and negative charge, right? The point P is at the same distance from both the charges. It will be getting cancelled out and it will come to be a 0. So electric potential at this point P is going to be a 0. So that's again a point to make a note. Well, now here we have done with the very, the first, part of this question, right? So let us, students, go with the next part. The next question here, it says, obtain the dependence of potential on the distance r of a point from the origin when r is very much greater than, r by a is very much greater than a, right? So, well, now here, if you just see, students, let me just take this Cartesian system, right? So we are knowing the same location, right? These are the charges are at the same location, right? So, well, let me just, students, once again, let me just put it here. This is my negative charge and this is positive charge. We know their locations, right? Now, students, if we just see what has been asked, obtain the dependence of potential on the distance r of a point from the origin when r by a is much greater than 1, right? So in the first part of this question, right, we had already got equation, right? Which is that equation, students? This is the equation that we have already got. V is equal to Kp by z square minus a square, right? And let us say the point P is on the axial line. So students, in that case, the electric potential that we are getting can be, students, plus or minus, both the values are possible, right? If the point P is closer to the positive charge, it will be a positive. If the point P is closer to the negative charge, in that case we are getting negative potential, right? Well, now students, here let us say that the point P is at any distance, okay, on that axial line or else on that z axis, right? So in that case, students, I can replace my z by r, right? I can just replace it by r. So let me just do that. V will be equal to plus or minus k p divided by the z. I am replacing it by r, so it will be r square minus a square, right? Now, what is the condition given to us, right? If r by a is very much greater than 1, right? So if you just see the condition, students, it's been told here, r by a is very much greater than 1. So can I say that r is very much greater than a? Yes. So this is the condition that has been given to us, right? So if I consider the point at which we are interested in finding out an electric potential is at larger distance compared to the a here in this case. A here in this case is from the O origin to the charges, right? So in that case, students, my electric potential will be plus or minus Kp over the r square. So this is what I can write it here under this condition, right? Now you can clearly see that, students, the electric potential is varying, is inversely proportional to the square of the distance from the center of the dipole here. Okay, this r that we are measuring is from the center of this at whatever distance on that z axis. A point to make a note. Well, now students, let us go with the third part of it. The third part, students, if you just see how much work is done in moving, work is done as, right, in moving a small test charge from the point 5, 0, 0 to minus 7, 0, 0 along the x-axis, right? And does the answer changes if the path of the test charge between the same point is not along the x-axis? So that is also been asked, right? Well, if you just see, students, let me just take again the system here, right? So we know that this is my negative charge at this some location. Here we are having a positive charge, right? If you just see, students, here in this question, right, we are going to focus on our x-axis, right? So the coordinates here that are given to us is on the x-axis. We are moving a test charge, right? So let us say that we are having a one coordinate here, okay? That is 5, 0, 0. We are having a one charge. Let us say we are having a small test charge here, Q0. Okay, let Q0 be a small test charge. And we are moving it from this coordinate location to a location of, let us say somewhere here, minus 7, 0, 0, right? So students, what will be the answer here in this case, right? If you just see, the electric dipole movement, students, we know that it is pointing from negative charge towards a positive charge. That's the electric dipole movement, right? Now the test charge that we are moving is on the, I can say it's like, the x-axis here is a perpendicular bisector to that electrical, electric dipole here in this case, right? Or else the point in the x-axis here is my equatorial line of this electric dipole, I can see, right? And students, we know that when you will be moving the, the test charge on the equatorial, at any point on the equatorial line, right, the electric potential that you will be getting here in this case will be a 0, right? Now, what does it mean, students? We know that work done, right? Work done is nothing but product of charge into a potential difference, right? That is, students, I can say here in this case, it will be a difference of V1 minus V2. That's the potential difference, right? So if you just see here in this case, if the potential difference is 0, right, we are moving from a one point to the another point, potential difference is 0. So that means, students, the work done here in this case will be a 0. So that is Q. Okay, yeah, let me write it here, right? So here in this case, students, if you just see here in this case, right, so we know that potential difference here is 0. So the Q into 0, the work done will be a 0, right? So, well, now, students, if you just see the second part of it, does the answer changes if the path of the test charge between the same point is not along the x-axis? What is the saying? Let us say, instead of moving this test charge along the x-axis, if you're taking the test charge, okay, like let us say some way, some other path, let us say like this, from, this point, okay, from this location to this location, right? So, why some other path, right? So will there be a change happening? No, right? There will not be a change, right? So I can write here a no here. The answer doesn't change because, students, if you just see the work done by the electrostatic field is not dependent upon the path, right? It is independent of the path, right? So here, if you just see, we are interested in finding out a potential at this points, right? When you move from one point to the another, right? So work done here in this case will be a 0, right? So that's the answer for this question. Well, now students, let us take another question. Now students, if you just see this question, a short electric dipole has a dipole moment of 16 into 10 to the power minus 9 coulomb meter. The electric potential due to the dipole at a point at a distance of 0.6 meter from the center of the dipole situated on a line making an angle of 60 degree with the dipole axis is dash. So there are 4 options here, and the value of 1 over 4 pi epsilon naught has been given to us, right? Well, let us quickly see that, students. First of all, students, let me write down the given thing here in this question, right? So I'll be writing it down, students, the given here in this question. We know that, students, the electric dipole moment is given to us. So let me write electric dipole moment is 16 into 10 to the power minus 9 coulomb meter, right? So we have given the distance at which we are going to find out an electric potential. It is at 0.6 meter. And the angle theta, that's the angle between the electric dipole moment and position vector, is given to us 60 degree, right? And the value of the k constant, or else 1 over 4 pi epsilon naught, has been given to us, right? Now to solve an answer for this, students, right? We're going to use the formula, right? Let me write down the formula, students, here. We're having the electric, the potential, right, is going to be, students, 1 over 4 pi epsilon naught, the electric dipole moment, cos theta divided by r square. So this is the formula, students, that we are having here. We're going to use this formula. All right. Well, let us quickly start solving this, students. Electric potential will be equal to, I know the electrostatic, the force constant, 9 into 10 to the power 9, right? And the electric dipole moment is 16 into 10 to the power minus 9 into cos of 60 degree divided by, students, it is going to be a 0.6 the whole square. Right? So if you just see 10 to the power 9 and 10 to the power minus 9 will get cancelled out. And electric potential here, we will be having 9 into 16. And I know, students, cos of 60 degree, that is a half is the value, right? I can write it here as a half divided by 0.6 square, that will become 0.36, right? So I can say 2 1s are 2 8s are 16, right? And V here in this case, students, right? 9 8s are, it is going to be a 72 divided by 0.36, and the electric potential at a distance of 0.6 meter, right, due to this electric dipole moment of 16 into 10 to the power minus 9, right, coulomb meter, will be, students, I can say 200 volts. That is what we're going to have the answer, right, when the theta here is of 60 degree. Now here in this question, students, a point dipole vector P is equal to minus P naught x cap is kept at the origin. The potential and electric fields due to this dipole on the y-axis of a distance d are respectively what, right? And we have been told to take the electric potential to be 0 at infinity, right? So if you just see in each of these options, we are given the electric potential and electric field, right? So let us quickly see that, students. If you just see here, I'm having an x and y axis, right? So what has been told to us in the question, students, right? We have been told that the electric dipole moment is this minus P naught x cap, right? Which means is that, students, the direction of an electric dipole moment will be pointing towards the negative x-axis, right? So this is my electric dipole moment vector P, let us say, is equal to minus P naught x cap. This is the direction of an electric dipole moment, right? Now, students, we know that the electric dipole moment, right, will be pointing from, students, negative charge, right? Let us say we are having a negative charge here on the positive x-axis and towards a positive charge, which is going to be on a negative x-axis, right? So that's the direction of the electric dipole moment we choose, from a negative charge going towards a positive charge, right? Now, if I just consider a point, let us say, students, let me just consider a one point on my y-axis. Let us say this P be a point on my y-axis, and let us say it is at a distance of some d, which I'll write it in the terms of coordinate, students, 0, d. Okay, so the point P is at a distance of d from the origin. Now here in this case, students, first of all, if you just see the electric potential, right? What will be electric potential? The O here, the origin here, I can consider to be as the center of an electric dipole. The point P is on the equatorial line of an electric dipole, right? which means that students, the electric potential will be a 0. Since if we just see the distance here of the point P from the positive charge and from the negative charge, it is at the same distance, right? So in that case, students, the electric potential, if we just try to find out, that will be coming out to be as a 0. Well, now students, what about an electric field? Now here in this case, students, when you talk about an electric field, right, we know that, students, electric field on the equatorial line, right, it will be minus k vector p over here in this case. It is a cube of r cube, right? Here in this case, I have chosen d to be as distance, right? So it will become dq, right? And I know the k is nothing but, I can write it here, the k is nothing but, students, 1 upon 4 pi epsilon naught, and this is going to be a electric dipole moment divided by dq. So this is going to be my electric field at any point on the the equatorial line of the electric dipole. So this is the answer for the question. Now if you just see this question, students, the electric dipole AB with respect to dipole moment vector dA is equal to minus 4 qa I cap and vector dB is equal to minus 2 qa I cap are placed on the x-axis with a separation r, as you can see here in this figure, students. The distance from A at which both of them produces the same potential is what? So that's the question here, right? If you just see, students, in this question, we have been given the two electric dipole A and a dipole B. And the question tells us about the electric dipole moment, right? If you just see, students, electric dipole moment for A, it is this minus 4 qa I cap, and for a B, it is minus 2 qa I cap. So looking at this electric dipole moment, I can very well say that for a dipole A, the electric dipole moment will be pointing towards the negative x-axis, right? So here they have used a notation of D as an electric dipole moment. Usually we use a notation B. Well, that's fine. We'll go with this notation, students. And here in this case for dipole B, we are having electric dipole moment, okay, also pointing towards the negative x-axis. All right, now students, what's the question here, right? The question here is we have to find out, students, the distance from A at which both of them produces the same potential, right? So what I do here, I'll be choosing a point P on my x-axis, and let us say that this point P is at some distance of x from the electric dipole A. All right, now to solve this particular question, students, what I do here, I know the, students, a relation electric potential is nothing but k electric dipole moment cos theta divided by r square. So this is the equation that we are having, right? So I'll be using this equation to find out an electric potential due to a dipole A and due to the dipole B, and then I'm going to equate it. All right, so let us start doing it. If you just see, students, electric potential at a point A, right, will be k. P here is a dipole moment, right? And students, that I will be taking it a magnitude of it. So that's the 4 qa here. So let me write it here, 4 qa into cos of, students, theta. Theta is the angle between electric dipole moment and the position vector. So here in this case, electric dipole moment, right? If you just see, it is pointing towards the negative x-axis, and the position vector is exactly opposite to that. So here the theta will be a 180 degree divided by distance, that is the x square, right? Well, now since cos of 180 degree is minus 1, so that will give me, students, minus 4 k qa divided by x square. This is the electric potential at a point P due to the dipole A. Same way, students, electric potential at a point P due to the dipole B will be a k magnitude of the electric dipole moment. It is 2 qa here, right? And once again, students, cos of 180 degree, right, divided by, why that 180 degree is very simple, students. If you just see electric dipole moment, students, I'll just show you here. Electric dipole moment here, its dB is pointing towards the negative x-axis, and the position vector that we have chosen x is towards the positive x, so that's angle here is 180 degree. Okay, that is how we are getting it. And here in this case, the distance at which the point P is, right, is going to be x minus r from the dipole P. So that will, students, x minus r the whole square, and that will be equal to minus 2 k qa divided by, that will give me a x minus r the whole square. All right, so things are done. Now from here on, students, we can just equate and we get the answer, right? So when I equate the electric potential due to the dipole A to the electric potential due to the dipole B, so what I'm going to get here is minus 4 k qa divided by x square will be equal to minus 2kqa by students, it is going to be a x minus r the whole square, right? So I can just cancel out whatever things here are common, right? I can say that first of all minus and minus will get cancelled out, it will become positive. So a gets cancelled, charge q gets cancelled, even k and k gets cancelled. So here students 2 1s are, and this is going to be a 2 2s are, right? So what I'm having here now, right? So you can see students, I'm having 2x minus r the whole square will be equal to x square, right? Now I can take out a square root on both the side, right? So taking students a square root on both the side, this will give me a square root of 2, and inside this it will be x minus r is equal to x. So I'm interested in x. Just open it up students, square root of 2x minus square root of 2r, that will be equal to x. I can take a x on the left hand side, just rearrange it, square root of 2x minus x will give me a square root of 2 into r. I'm interested in x, right? So I can write students this x to be has a square root of 2r, and I can take out a common here, right? The x, and inside the bracket what I will be having, it will be coming here in a denominator, it will be a square root of 2 minus 1, right? So that's the answer for this question. If you just see students, the x is a distance at which we will be getting the same potential, right, on the the x-axis due to this dipole A and due to this dipole B at this particular distance. All right, so well, that's the answer for this question. Now here in this today's session students, we have got an equations of electric potential due to this dipole, and these are the equation students that we have got, right? And if you just compare this electric potential with the electric field due to the dipole, right, I can clearly say that the electric potential is varying inversely proportional to the square of the distance, and electric field is inversely proportional to the the cube of the distance, right? And students, one more point to make a note is that the electric potential on the equatorial line of the electric dipole is going to be a 0, whereas the electric field on the equatorial line of an electric dipole is a non-zero value, right? And even if you compare this electric field on the axial line, it is 2 times the electric field on the equatorial line. So these are the few points to make a note from this today's session, and this is all for this today's class students. See you in the next session with some other new topic. Till then students, bye bye, take care, keep learning, bye bye.